Okay, resonance structure we are going to see. There are many organic molecules whose behavior cannot be explained by a single Lewis structure, right? It's given like that. Benzene is given as an example. You know that benzene structure. Okay, so here C to C single bond, right? So and then C double bond will be alternates, right? Like this. So there are alternating C double bonds, and then what it is given. Okay, so it this is benzene characteristics. Benzene that you know, right? Okay, so benzene should exhibit two different bond lengths. So C to C single bond, C to C double bonds. Okay, so it can be uniform, like C to C bond is the bond length is 139 picometer. Okay, a value intermediate between the C to C single bond and the C to C double bond. C to C single bond is 154 picometer and C to C double bond is 134 picometer. So if you take an average, like it is nothing but it is like a middle bond. Okay, so you must understand. So the average bond length is 139 picometer. So structure of benzene cannot be represented by the above structure, but it can be represented by identical structures like that. You can either put double bond like this, so 1 to 2 position, 3 to 4 position, and 5 to 6 position, or else 6 to 1 position, 2 to 3 position, or 5 to 4 position. You can either write these two structures. So these structures should have same, benzene formula, but it should have some resemblance in it. So it is known as resonance because I will explain you what is resonance actually. Suppose if there are chemical reactions takes place. Okay. So what is the chemical reaction? You know that the two reactants combine to form a molecule product. Okay. That product might be of any one of these two forms. Okay. Once it will become like this, again it will become like this. Okay. So it will be of different forms. So either this form or that form. Okay. So we couldn't predict whether this form is the product, that form is the product. So in between these two canonical forms, these are all said to be canonical. What is canonical forms? It might be either this form or that form will be formed for benzene. So the double bond will be shifted in some other places. That is the major difference. So in between, we can choose some other common thing. So that is known as resonance structure. See here. So what is the resonance right now? So we saw two canonical structure, right? What are the two canonical structure we saw? See, for example, so we saw like this, right? These two canonical structure. The bond will either this way or this way, right? Okay. So out of these two forms, we can predict any one hybrid out of these two. Okay, we can provide some hybrid structure. So that structure is known as resonance structures, and these two are known as canonical structures. Got it? So the resonance structures or canonical structures or contributing structures, we can name it either way. These are hypothetical. Yeah, and individually do not represent any real molecule. We are, for our own, we are writing this structure. It might be like this, it might be like that. In order to get an idea, so we are using this resonance structure. Okay. And then definitely contribute stability, and then its structure is in proportion. So this resonance structure, which is in proportion, it contributes definitely a stability to the compound. So another example it is given. What is that? Nitromethane. Okay. So what is nitromethane actually? So what is it? Nitromethane. Nitromethane's formula is given. Okay. And then you have seen two structures, right? See here, Lewis structures also representing the molecular thing. Okay, it is representing the molecular thing. But you should understand, what do you understand? The first structure and the second structure, these two are canonical structures. See the shift of the double bond. So here, right? Okay, these two, the double bond may be upper side or lower side, right? There are two oxygen in that. So that is the case. So this NO bond of nitromethane are of the same length. That means intermediate between a NO single bond and NO double bond. Okay. So the actual structure of nitromethane is therefore a resonance hybrid of the two canonical forms. Now you got the point, right? So as we have seen in carbon, in carbon-carbon single bond, the bond length will be 154 picometer. In carbon-carbon double bond, it is 134 picometer. But we are providing, on hybrid structure or hybrid thing, in between, that is 139 picometer. Picometer means you know that 10 power minus 12 meter. So here also we are understanding the same for this nitromethane. Okay. So by developing this kind of resonance structure from the actual structure, okay, this is called the stabilizing product. How it is known as stable product? The energy of actual structure is lower than that of the canonical structures. Got it? So the difference in energy between the actual structure and the lowest energy resonance structure is called the resonance stabilization energy, or simply the resonance energy we can represent. The number of important contributing structures, the more the resonance energy. It is particularly important when the contributing structures are equivalent in energy. That is also we make sure. We make sure both the thing will be in equivalent. That means actual energy and then resonance energy. So there are rules applied. That means resonance structures. If you want to draw a resonance structure, suppose if you are interested to learn, masters in chemistry, you are finding some research in chemistry. You are finding some new molecules, okay, organic molecules or organic compounds. Suppose if you are getting sometimes one structure, sometimes other structure, sometimes it might be ozone and all. It has three canonical forms. The ozone has three canonical forms. Here, that ozone is nothing but simply a molecule. Here, it is organic compounds, right? So either this way or that way, it might be occur. Okay. In order to get the resonance structure, what you need to do, you need to follow all these guidelines. Resonance means hybrid structure from that particular two canonical forms. Okay. It should not violate all the rules. It should be reflecting those two canonical forms, and then even then from the actual energy, this particular energy requirement is very less. Resonance structures, in order to if you construct a resonance structure, then the resonance energy will speak of. That is efficient, and then it is stabilizing. Then the same position of nuclei, you must understand the position of the nuclei is same. First point. Second point is same number of unpaired electrons. Got it? So among the resonance structure, the one which has more number of equivalent bonds, all the atoms with octet of electrons, that is except hydrogen, which has a duplet. Okay. Yeah, except hydrogen, remaining has duplets. Okay. So they are under covalent bondage. So resonance structures means the one which has more number of bonds, covalent bonds. That is, you have to see to that. Then less separation of opposite charges must be there. Okay. A negative charge, if any on more electronegative atom, a positive charge, if any on more positive atom, and more dispersal of charges more stable than others. Got it? So that means what is that? Less separation of opposite charges also it should have. If the opposite charges are highly separated, then we can't think that as a single compound. It extends some polarity. It will not speak of. Okay. That's why. So write the resonance structure for CH3COO minus, it is given. You can make it. Like this. Right? CH3COO minus. Here also, you could have seen what? C2O single bond and double bond. The resonance might occur like this in organic compound. The single bond and double bond, it might be occur like this or this. Okay, you are writing the resonance structures. Got it? So similarly for CH2 double bond CH-CHO also, it is given. The resonance structure is like this. The double bond may shifts. Got it? See the structure. Which one is more stable? You know the form actually, which is having more covalent bonds. Just count the bonds, which is having more covalent bonds. That is, each carbon and oxygen atom has an octet and no separation of opposite charges, right? What is the first structure? It has more number of covalent bonds. Then each carbon and hydrogen, okay, has no separation of opposite charge, like delta plus minus, like in this you have seen like that, right? Plus and minus. So this kind of opposite charges or polarity, it will be a real separation from that two atoms, right? So there must be no separation between the opposite charges. So that is the case, most stable case. Got it? So when compared to all these three, first is stable, second is less stable when compared to one, third is again less stable when compared to other two. Okay, in second one, negative charge and more electronegative atom, and positive charge and more positive atom, that you know, right? And the number of bonds are higher. Okay, but here, what happens? Third does not contribute as oxygen. It has positive charge, right? Carbon has negative charge. So it is less stable. It won't be, less stable means what? It won't occur for more hours. It will not be a permanent product. Okay. Same way you can see this structure also. Okay. See through this first and second structure of CH3, COO, CH3, ester. Okay. Then we saw that resonance effect, right? So what is resonance effect? The polarity produced in the molecule by the interaction of two pi bonds, right? You know about the pi bonds right now. Okay. So what is pi bond? You know, right? Lateral connection, lateral bonding. Okay. If there are pi bonds, right? Two pi bonds. Okay. So the resonance between okay, the transfer of electrons is away from an atom or substituent group attached to the conjugated system. Okay, atom or substituent group attached to the conjugated system. If the transfer of electron is away, then this electron displacement makes second position in the molecule of high electron densities. This effect is in anil is shown. Okay, you know that the two bonds, two pi bonds, it provides polarity. Okay, it produces polarity. So that is what, how the polarity will occur. Either the electron is moving away from the atom or substituent groups, or it is towards the atom or substituent groups. By means of this transfer of electrons away or towards, it creates some polarity. So this makes sense in positive resonance effect and negative resonance effect. For positive resonance effect, if the electrons are moved away from the atom or substituent groups, then that particular atom or substituent groups becomes positive. So that is plus or effect. Got it? If the electrons are moving towards the substituent group or moving towards the atom, then that is minus or effect. Got it? So these two are clearly explained. See the, arrow marks. I've already explained all these things to you, right? So that fish hook arrow marks, that long arrow marks, everything. How the bond is shifted over here. This double bond to single bond, double bond is cleavage, and then it is shifted to the next, right? Like this, you might have seen the direction also, right? The direction is reverses. The electrons away from the substituent group. See here, away from the substituent group. Right? See here, towards the substituent group. That is the difference. Transfer of electron in this positive effect, aniline, towards the substituent group. In nitrobenzene, negative effect, negative OR effect will be there. It is, sorry, in aniline, it is away from the substituent group. Electrons moves away from the substituent group. In nitrobenzene, electrons moves towards the substituent group. Like this. This is the major difference. This is plus or effect and minus or effect. So plus or effect aniline is example and minus or effect will be having nitrobenzene as an example. So there are so many electron displacement group is given, so for which is obeying plus or effect and minus or effect. You better go through this. This is very important for your classes, for your exams. Okay, then this you know, and then we'll see electromeric effect. It is a temporary effect actually. The organic compounds having a multiple bond, double or triple bond, show this effect. Got it? Only double or triple bond. So it is defined as the complete transfer of a pair of electrons, pi electrons. That is very important. To one of the atoms joined by a multiple bond. Okay, on the demand of an attacking reagent. Why it is on the demand of an attacking reagent? Whether it is nucleophile or electrophile, we don't know, right? So on the demand of that, the electrons may the pair of electron is completely shared between that particular atoms and the constituent groups. Got it? This effect is annulled as soon as the annulled as soon as the attacking reagent is removed from the domain of the reaction. That is also very important. If the attack, so we are going to see in class 12, like SN1 reaction, SN2 reaction, like that. Okay, nucleophilic substitution reaction 1, nucleophilic substitution reaction 2, like that we are going to see. So here, when other atoms join to, when other atom tries to combine with that particular compound, then this attacking reagent will go away. Like that, it is removed from the domain of the reaction. Got it? This is very important because it does not hold that amount of atoms within that particular 4 substituent places. So, in order to add much more, this reagent, this attacking reagent will be removed. Got it? So it is represented by E. This is the electromeric effect. Got it? So represented by E, that is shifting of the electrons showed by a curved arrow. Here also positive and negative. This effect, the multiple bond are transferred. Okay, the multiple bond are transferred to that particular atom, to which the reagent gets attached. That means pi electrons, you know, they completely share the pair of lateral connections. In lateral connections, that means perpendicular to the plane or lateral to the plane. Okay, in lateral connection, there are pi electrons, shared pi electrons. That completely shared pi electrons is now transferred. After multiple bond, okay, it is now transferred to the particular atom or substituent groups, to which the reagent gets attached. Reagent, where the reagent it is, whether it is in electrophilic center or nucleophilic center, that electrophilic or nucleophilic center is known as atom. Okay, so that atom or substituent groups. Now see this reaction, it is attacking reagent. Okay, this is attacking reagent. Okay, now what happens? This bond is shifted. That means in this bond, not like plus and minus. Okay, if the bond is cleavage, if plus and minus will be there, that is inductive effect. Got it? Isomeric effect, you know, that is the resonance structure. It represents the resonance structure. In this electromeric effect, totally like a homolytic cleavage. totally both the electrons are shared from the multiple bonds to the particular atom where the reagent is attached. Got it? That reagent might be nucleophile or electrophile based on the centers, electrophilic or nucleophilic centers. So here, after that, the reagent, I mean, if the reagent is there, okay, then that is positive. If the reagent is removed, does not get attached, then that is negative. Got it? This is very important topic, electromeric and electromeric effect, that is positive and